Richard was one of only 4 fellows at Ford. He just retired there after 25 years with the company. He is the architect of their PLM and ERP infrastructures, and one of the most widely read, widely informed, and knowledgeable people in our industry. He's been a regular at COFES for several years, and he adds a great deal to the conversation here. So I encourage you to engage with him in the hallways that we have constructed for you here. Richard's education is all from the Technion in Israel. He has been on the faculty of Georgia Tech. And now let me just turn the mic over to Richard Riff. Please give him a warm welcome.
Thank you. Thank you for having me here. It's a great honor, and I will try really to keep you interested for the next hour. The reason I really was glad to be invited here, for quite a few years I am trying to tell few of you during discussion that engineering is not only about engineering software. Many times, and many people here are presenting a great solution of engineering software to do engineering. But this is really only one part of what your customer, the engineers, are doing. And I would like to present a bigger picture of how you do engineering and how engineering software is being integrated to that, and some combination between really risk, decision analysis, decision making, and engineering software. In this case, we pick up really design verifications, both physical and virtual, but we could pick any other of the engineering software you're working here on. So what we will discuss is really, first and overall, decision analysis, which is really, I was hoping that I would have really the TV working, but it's okay. Which really is the craft of rational decision makers. Really, it's part of really making engineering work. Engineering is nothing else but series of decisions. Series of decisions you need to make. And as you will see, many times we are not so strong in this particular way, which is the engineering. And then really we'll try to see how we are incorporating really this risk or design or really decision making into our really engineering work. So first of all, decision analysis. How we manage risk at Ford. This is the idea really which we are trying to do. So we have investment in life cycle in manufacturing industry, and I separated it here between planning and executing, where the decision to move from planning to execution is there. And we strive on execution quality. So first you do simulation and verify really your design to move, and really they are supporting the decision really to move. And then really you strive for excellence, and you have the tools during the execution. Tools like Six Sigma, which really you can evaluate really any of your designs and correct in systematic ways. Very, very rational tool, very powerful tool to do that. Or we did in IT something we managed really risk, which few of you were complaining about, really, we manage really to do a management or decision about the number of licenses we are employing. Normally, you buy licenses to the maximum number of your simultaneous user. And then you are covered. But then you are overpaying, really, because in reality, there is very, very few times you really need all those licenses. If you do a calculation and accept, for example, 1/10 or 100% of refusal to simultaneous licenses, you reduce the number of licenses by very big number. And agreeing between the users and IT on this, we save really almost 40% in our expenditure on CAE licenses. So here is how you make decision during really the operational part. But this is not what really we wanted to discuss today. Today we want to discuss really the decision during the planning part. Because it's a series of decisions you need to make really to go from really the planning to the execution. We all are starving for excellence in execution. Let's see how we are doing it during the planning period. So to present that, I want really, and to give you the idea, I want to present you, and Joel already kind of gave my really age away. So I want to present you a game from the 60s. Very, very famous game. So those of you which know the game, please don't tell the answer to the others. Monty Hall problem. And the Monty Hall problem, you have really a game where 3 closed doors, where the host, behind 2 of them, you have a goat, Molly and Mo, and behind the other one, you have my car, the Shelby. And you are asked to pick one door by the host. Choose one. You make your pick, and now the host, which know really, once you made the pick, the host which know really what is behind every door is opening one of them, which have a goat behind. Mo and Molly, doesn't matter. And he is asking you, given the option now, should you switch your pick, yes or no? So let me ask you the question. How many of you will switch? About 1/3. How many will not switch? Big majority. So let me tell you already the answer. You are dead wrong. And by the way, the same results you are getting in any engineering kind of meeting. The same result. The results are about 3/4 will not switch, will hang on to their decision, 1/4 will switch. So we can run really this discrete event simulation, very, very simple, and to find the answer. And the answer is, of course, once you are running it, and I will explain it later on, is that you should have switched by serious margin, as surprising as it sounds. And this is really, here is the results, 76 to 24%, really, which we presented to Ford management at some point of time of the decision. And you could see here in the room that there were the same kind of results. And to show them why they need decision analytics, why they need the decision process, and why we need to edit, not only for decision which are financial in a sense, but also for part of the PD decision process, the design and verification of it. Why we are wired to go error? So humans are quasi-rational. Most of the time, we don't recognize really the uncertainty. And when we do, we process it very poorly. We don't deal very well with uncertainty. And normal decisions, let's be frank, during the planning stage, you are very well off if you are 60-40. Forget the 80-20 rule. It doesn't exist most of the time. 50-50, 60-40, you make decision. So you need to deal with uncertainty. And we oversimplify. We focus on very extreme scenarios. In vehicles, in aerospace, everywhere. We take the worst case scenario and processes according to the worst case scenario. And apply experience really, we know it's this way. We also overemphasize current expense on the future really. Once again, we use heuristic, strong biases. Why would I switch? I made my pick, let me stick with it. Focus on end really state rather than on the path, how we are getting there. And don't see where the process is leading us. And to minimize the damage, what we do, awareness, quantitative decision tool, decision process discipline, and so on. We are disciplined. It's not that we are not disciplined. We keep the discipline, but with the wrong decision. Why decision go bad? We trust our intuition, we trust our ego. We have great solution to the wrong problem. We have no choice. We reject alternative. Ignorance is a bliss. Our forecast failed to materialize. How many times you heard this one? We got what we asked. We just don't like what we got. Our strategy retreat was a train wreck. So you have bad methods, you have a bad frame, you have bad alternatives, bad information, value disconnect, and no commitment. This is why really the decisions are going bad. And pick your really medicine here. What is a good decision? Good decision have really required due diligence in the 4 areas. You need to have the appropriate frame. You need to be creative, doable alternatives. You need to work on your alternatives. Otherwise, it's not a decision if you have only one alternative. You need really reliable information to the amount you can get it. Clear values of trade-offs. Logically correct reasoning, and we can use here different tools, and commitment to action. Without commitment to action, forget the whole process. So those 6, really, you tend to have 100% of them. You will never do, you see here the picture, but at least you should know where you are. And what really makes decision-making hard? Why it's hard to make a decision? You have 2 complexities. You have the technical complexity, and you have really the social complexity. So technical complexity is the uncertainty, it's too many parameters, sometimes conflicting parameters, confounded values, complex dynamics moving, and really subject matter complexity. Many of the projects really I have really experience with, the missing part was the subject matter expert. Really to have the number, Ford Motor Company, GM, Boeing are huge companies until you need a specific answer to a specific problem. Then you are getting always to the same one person name. And then you have really the social complexity, varying attitude, values, belief, different frames, organizational structure, which really prevented. Time dimension. You need to make timely decision. So thinking about it, the Monty whole problem, you see where it's located. We are to hold the company picnic. It's mainly social issue. Should I accept offer on my house? I wish. This is more technical complexity. And really, should Microsoft buy really Yahoo or something else of this kind, which have both of them? To deal with technical complexity, we have tools: simulation, discrete event simulation, which I just saw for the Monty Hall problem, the trees, AHP, probabilistic, different tools really to do the trade-off and decision tree and so on. For really for the social, we have facilitation, team building, brainstorming, focus group, interview, and so on, which we are dealing with. And now, really, in the most complicated problems, where you have both of those complexity, you need the decision analysis. And this is really the problem which are interesting problem. So what is this decision analysis is? It's a well-established scientific discipline. Unfortunately, we don't, in engineering, don't recognize it so much, which really sharing root of economic and combines normative decision theory with element of psychology to prescribe rational decision-making practice. And what I told to my management at that time when we really kind of pitched to them to go this way was one thing. Guys, we will not provide to you always the right really decision. This is something which will not happen. All we are providing you is the tool to make more rational and more probable decision to be right. It's almost like a casino. Casino will always win at the end. Why? The probability of you can win as a person against the casino. But when you total all the people, all the games, they will always win. And it's exactly the same about that. If you will total all the decision making you need to make, at the end, you are making better decisions with that. This is all. So the decision problem is characterized by option, uncertainty, preferences, and the process for consensus, combining using really expected utility and playoff, use structure iterative process to identify new options, select more rational set, and facilitate to get buy-in decision from both stakeholder and subject matter expert. So you need really a team. And we're trying to present here the team, how the decision dialogue is done. You have really two groups. You have the decision board, or the decision makers or decision maker, and you have the project team, the subject matter expert. So first of all, you need to recognize the situation that you need to make some decision. You give to the team the ability to assess the situation and really understand it. Then they create a frame for the decision, you need to approve it. Once you have approved the frame, the team is developing the alternatives, and you need to approve them, the board. Once the alternatives were approved, you evaluate them, do the simulation, make a decision, and plan for implementation, and then approve the plan. Very simple process, which is very simple to teach and to play again and again and again. And of course, you don't need maybe all the steps all the time, but most of those steps you do. So now, really, I saw in your eyes, he ran some kind of discrete event simulation, and he's telling me stories. I'm still sticking with my solution. So let's analyze it, really, the approach. So here it is. Don't switch or switch. Very simple. The most simple, really, if you think about this decision. If you don't switch, what you have is one of them was exposed, Molly or Mo, correct? And really, you have now your ability to get the car behind the door you pick is 1 to 2. Nothing else. This is what you are left of. If you switch, let's start with the 1/3, 1/3, 1/3 to begin. The first one, let's say the switch, the car, moly or more was exposed, correct? And if you switch, you are getting more and more on moly again because you pick the car, one against you. On the other hand, if moly was exposed, more was exposed, okay, you have moly ahead of you, in front of your pick, you switch, you got the car, one for you. If you pick more, moly was exposed, so you're okay, you again have a car. So you have two times the car, one time moly or more, which is 2-to-1 or 2-to-3 probability, 2 out of 3. Very simple analytic consideration. I did not need it really to run the simulation of really the events, but you can see that this is exactly what we will now use to convince you really that we can use this kind of decision and this kind of really part also in PD, or product development and verification. Decision analysis, it's really very established discipline, and those of you which won all these institutions and so on, we personally sent quite few people to Stanford to get really to get the classes, and they taught really at Ford quite few people in these practices of decision analysis. I want to give really a good example. Decision analysis is done in Chevron now for quite few years. What they did, they recognized the value in the 90s. They trained about 1,000 of their executives for 2 days, very intensive 2 days of seminar, and the dozen of decision support staff were really trained in Stanford. And really the decision analysis at Chevron now, they build a consulting organization. They have about 2,000 really executives which are making the decision, and about 100 internal consulting staff really engaged. And they have significant benefits out of it. Not only a common language and expectation, common culture, shared understanding for good decision, but also a very systematic way of making decisions. So hopefully I did with you what we were semi-successful doing with our really management, and convince you to go this way to the decision analysis. Now let's see how we are integrating it for design value, really, to make the right decision during, let's say, a verification process. So let's first look what is the challenge and why we need decision analysis, why we need all the help we can get. When you're looking really, there are 2 factors which everyone today in the manufacturing world and the industry is looking. You're looking on productivity, do the same work with less people, or do more work with less people, even better equation, the productivity part. And all of you will jump now and say, oh, my tool is providing you productivity. If I will count only the productivity of the different vendors of tools, of engineering software tools, which pass my office in 1 week, I don't need engineers at all at Ford, to be frank with you. But really, the other part is the efficiencies. And the product development budget, you have 2 major parts. And I was trying to symbolize by the number of dollars without giving you the real numbers, really how heavy it is. You have the tooling design, you have the plant installation, you have all the other expenses. I don't want to touch this part. The part we want to touch now is the one which is product design and manufacturing verification. You have a design, and you want to verify it, physically or virtually. And this is being divided. This part I want to address now, the value there, the efficiency which we can create there. It's really, if you are looking on verification, you can really divide it into 4 major groups, which we'll analyze. You can have design standard, cost you no money, very easy. You know what you are doing, you document it very well, and this is it. You can have a CAE, as you can see, $1 single there. You can have physical prototypes, and you see the number of dollars there, and you then have a physical testing for them. So this is really kind of the efficiency you want to do. And the answer, looking just on the number of dollars, is obvious. The question is how you are getting there and how you are making the right decisions. So what are the efficiency opportunity? I will not bother you too much with this. It's CD for the whole vehicle. It's CD for the component level, like antenna and so on. It's the thermocooling. It's the new fuel economy technologies, battery management system, performance, and so on. There are many subjects where we can do really this kind of exercises of decision analysis and really get efficiencies. And all really are included in design verification. If it's a vehicle prototype, subsystem prototype, physical testing in wind tunnel, dynamometer, CE, or design rule. Here is the whole thing. And this is what we want to do. Of course, the answer is obvious to every one of us. The normal procedure is you have the requirement, you have some design rules from the experience and really the model you did before. Those are very few. You have limited use upfront of CAE for verification. And most of it you are doing during you are testing and verifying. This is really where and the most expensive part, and this is most of the work which is being done. Of course, you want to reverse this. You want to have the most to handle through design rules from really the generic design verification processes. Then the CAE, all the physical testing, and really through failure mode analysis to correct your really generic design verification to have rules. Normal, really, whole system engineering, the classical one, to correct it. This is all we want to do. It sounds simple. It's not so simple, and the answers are not so obvious. So we need a method to know. The most important method and the most kind of decision and eliminating the risks through this whole process is how we choose which method to use. Test, CE, both, none. Okay? When is design good enough to stop testing at all? What is called in the industry zero prototype. How sensitive is the decision to program content, to assessment of confidence, to the total cost, because at the end you judge it with money. You do it for business. We need a method to know how much is at risk. Calculating the risk every time is the right thing to do. Why? Very simple. We, all of us, or most of us, are buying insurance. And we decide the premium on the insurance to pay according to the risk. I just moved my house from Michigan to Florida. Guess what? Now I am at risk of flooding and hurricanes. I have completely different insurance plan, different premiums. We are paying for avoidance of a risk. This is exactly what we do. This is exactly what we need to do in engineering too. We exercise it very well, by the way, in our private life, or our private decision. When it's getting to engineering, we don't do this evaluation. At the end, it's a premium which you pay to be really confident that you have risk avoidance. This is the whole thing. For given the design verification plan, what are the residual, the unmitigated risk, how you deal with it, and the most important part, where we do invest first. Which process, method, or tools give us really the best payback. We need to realize that two things are final in engineering: time and money. Those two are final, and the engineers normally stop working when one of them is finished. They work until the time is finished or the money was finished. But those are finite. So we discussed the decision, really analytic discipline, analysis discipline, and we are now going to use this problem to do it. And the first thing, really, which I want to give you an example, is the Bayesian inference. And in a second, you will understand why, how I am going to use this tool in making some of those decisions. So let's assume that while you were away, the swine flu virus was back home, and you are coming home, and the likelihood you should get a flu when you get back is 1%. And there is a test to see if you are infected. It's about 95% accurate, but very expensive. Doesn't it kind of sound like exactly what we are doing in engineering? Okay, I have 1% chance. The test never is complete, never 100% accurate. We need really to evaluate the accuracy of this test and to know it. And normally it's expensive. So what you do? Should you take the test, yes or no? I will not test you this time. But if the test is positive, what is the likelihood that you really have the flu? Because this is really what it is about. You don't test for testing. You want to know what is, okay, I did the test. Do I have the flu or I don't? So we can analyze it using Bayesian inversion. We can really take, and I will not go to the details, those of you which will be interested in the detail, how you really do it. You go really, yes, no, what, and really reversing the real result are showing. And the main point I want really to get your attention is that if the tests come positive, and you're looking on the number, you have 84% chance, 5 of 6 really, that you don't have the flu. It came positive, but you have 84%, you pay for the test, went through the test, 84% that you don't have the flu, even so it came positive. And many of us which are going through tests like this know this reality. So should you take the test? Of course, here is the premium and the risk. Depends on what you are willing to pay for the false positive. You got 84% of false positive, but if you are willing to pay because of the 1% risk, here it is. So let's now translate this question into a real-life question. To test or not to test? And we took a number from real program. Small but real program. You have 80,000 units per year, small program. The physical test cost is $3,750. The CAE cost is $2,500. You believe that there is about 30% likelihood you will have an issue. From experience, from design rules, from everything else, you know that in this particular design, you have a 30% plus minus chance that you will step into an issue. And the odds of detecting the issue, or the accuracy or the confidence of the test, are 70% for the physical test and 50% for the CAE. By the way, real number from real case. I just kind of, with Brad advice, took the real case out, not to punish the innocents. And the redesign cost The retooling, it's a fixed cost you $37,500. Repair, 8.75 per unit. Cost of the whole design, verification, redo, because if you test it and it's failed, you will redo it by definition. This is the real cost. And the potential warranty cost in green there, because it doesn't belong to the direct cost, is $108,000. And now you have the numbers and the risk and the numbers, and you can play with them. And the question we always ask now the engineer, okay, what is your design verification plan? You're running now a business. You have finite money, finite time, finite money. You cannot test everything. So some of you will really see this with a surprise, but not testing is sometimes a very rational choice. You have we calculated here the program, physical test cost, CAE, 60% likelihood of issue. I kind of enlarged it just to give better representation, and odds of detecting is about 75%. Redesign cost, you can see and the risk, the warranty is really $55,000 across all those units. And the question is if to do tests in this case, and then of course, just to examine our logic, what if you have a better test probability, failure detection of 94% versus the 60%? Let's examine how really sensitive those decisions and those risk mitigation inside are to our confidence. So the decision tree is very simple. Test yes, no. If no, no, zero cost. If yes, you have the business impact, the retool, and so on. If you are testing, yes, the cost of the test, the fail, pass. If it fail, the retool. If it pass, the test indication, redesign, and etc. And here are really the cost. Remember, the failure likelihood is 60%. So the business impact will be directly $55,000 of the warranty. On the other hand, if you did the test, $5,000 for the test will detect 75% of the problem. So if it fails, you have $283. And of course, we always redesign if test indication is failed. And we can really run now what affects the decision. And what affects the decision is, of course, the value of the branch, how much you pay for, and what is the expected value you will receive out of it. And the value in this time is saving the money. And of course, really, you want to know how much unnecessary redesign you did and how much you missed the failure. And looking on all those numbers, the rational things to do, as you see the numbers, is not to test. Take risk of a failure. Failure is a possibility. It's not always the worst solution. On average, we shall do better. Of course, assuming that you don't have any other issues, like really the customer you will be losing, or if of course it's really safety, immediately you will do the test because you don't have a choice. But what if the likelihood of detection was higher? We just now took it to the 90%. And you see the new number. The false positive now was reduced from 16% to 4%, and the missed failure was reduced from 31 to 9%. Now it makes sense. Let's test. So here is really how you are analyzing the risk and what you do with it. The test is the rational decision. So sometimes you don't, sometimes you do. From where those probability came, very the case we just inverted, did really the design goodness. You see the good and the 37.4%. Really the probability design is good and the tests say pass. It's 40 multiplied by 94%. Then this is what we need. The fail 58.7%, probability there. And of course, the bad, the 9.4, probability of design best pass. Very simple inversion. And to make it even a little bit better, so the period, the likelihood, the post-period, and the pre-period, which is the important part. The post-period probability is really, from the periods is the Bayesian inversion, which we took before, and really this is how you find your answer. But to make it much easier to our engineers, we did something else. We calculated all those cases, we did them, and put them in a very simple template. You can see here, the template is very simple from really to play engineer on. You have really one is really the test confidence from 1 to 10. And on the other hand is really the failure probability. Very easy. And you can see how, for example, at certain point of test confidence and probability of failure, which we discuss, the 60%, really, if the test confidence is getting higher, how really you are moving from don't test to test. And vice versa. If you know really that the likelihood of failure detection is 50 or 60%, you are completely in the green. Don't test. Our engineers now are running those kind of analyses, put the point, and making rational decision to test really where the money they put behind this is paying off. Of course, do you feel lucky if you don't test? Your net cost is 0. In this case, the odds are 60% in your favor. And of course, if you fail, we calculated, it's 288K. Good luck next time. But at least you know what you did. Of course, the risk of running tests and passing is cost of the test, the risk of false positive, downstream cost, customer impact, which is very important, the cost of test, the cost of redesign, the risk of false negative. The false positive and the false negative are really the key issue for the decision, really, in your evaluation. And the way we are doing it, we have design verification really model, which we developed, which is, by the way, patent. And we are examining all the cost, really, associated with the DVM, our confidence in the design verification methodology or model, likelihood of failure, business impacts through all this, and the cost to redo it. And you go, and really there is a very simple simulation. You put your numbers, which are given, play the analysis, and you are getting at least not the right answer, but probably a better answer. This is it. So in reality, it's really a little bit more complicated. The decision analysis process at fault is starting really with the requirement. Subject matter experts are providing input, the decision parameter for generic design verification plan. You have all the DVMs, all the design verification methods. You have really the requirements, which are coming from the system requirements. You do overall DV plan, risk analysis generated. We just talk about it, and we will see good example immediately, like real example of this. What are those really analysis, what this analysis is generating? We have the analysis tree. I think it's only partial here. the detailed DV risk analysis by requirement computed. And at the end, it's end up in those kind of really very simple test or not test, and the next one you will see immediately what to do, CAE, test, neither, and so on. So let me go to a very, very kind of, I would say, one small example. Really, I didn't, on purpose, I didn't bring the big stuff or something which is proprietary to Ford. As a retired person, I need to be very careful. But it's really a very, very nice example, which I follow personally through the years. Air induction system. The air induction system have the tendency in the Rust Belt, not here, to get accumulated with the snow. And the snow is accumulating in the duct and really bringing the power to power loss and stall. Known phenomena, and when, during my time as a chief engineer, pre-PLM, what we did, we sent the vehicles to the Upper Peninsula with the drivers, and they were driving really in front of the snow, hoping that the snow will get accumulated and see if they stall. If they pass the test of driving through a snowstorm. If they were successful, they got frozen. And if they were not successful, you know the answer. Then we really created, we said, just a second, you don't need to do that. We created a really test simulation on the dynamometer and really snow guns, really pointed to the grill, shooting it off and testing. And still much less expensive than going to the Upper Peninsula, but still pretty expensive, as you can imagine. We did analysis of that, really what's going on. And this was ongoing, and one of the reasons was also the lack of really very good design analysis method, mathematical models. So we did the analysis and saw how much we are paying for the false positive and the false negative, which are really where you are hurting. You can really see the whole analysis tree, or sorry, only part of the analysis tree I am showing here, because I didn't include really the lower part of it, but to show you really what we are looking for. We are looking for really calculate the numbers of the real cost in this case, and looking how much the false positive and false negative is costing us. And here is the cost and risk analysis as done. So you can see here, we went and really the pre-DV process, the redesign cost, the repair cost, the warranty, and the total cost. In the 4 cases you can apply. Do nothing, and we saw already that it's alternative. Test, CAE, or both. Which one should I pick? You're looking here on the total cost, and important part of cost not to be forgotten is the green, the warranty, because you can see. And very easily, the rational choice will be the option with the lowest expected net cost, which in this case is the CAE. You can see it very clearly. Not the test, the CAE, at this case. And why the test is less attractive? Because of what we just mentioned, the cost of the false positive and negative. You are paying too much for something really which you don't need. Contrary, is really inhibitor in your decision. So let's analyze this case on this very simple table. And this table was like the test or not test table, was really designed the same way. On the upper side, on the horizontal, you see the confidence in CAE. The highest is 1, the lowest is 10. 10, it's really 50-50. a flip of a coin. This is, sometimes it's come to that. And really, here is the likelihood of failure on the vertical one. Bad or good? The good part, of course, is on the corner there, up left corner. This is the nirvana. And in the past, we did the test. You can see that. I just show you that really, with the increased confidence in CAE dividend, at least 5, this is all we needed. And it was very well defined through this analysis. How much really I need to develop in the method for CAE to have confidence at least of 5. Because if I have 5, I just move here. This is it. So I know exactly how much I need to pay. It's not the story anymore of this CAE vendor which is coming to our office and telling, oh, we solved the world for you. I know exactly what the confidence I need, what I need to pay and how. And really now the question is, if to reduce the failure likelihood to 10% or less, we will be able to implement it through design standard, do nothing. So for example, here is the system. And you can see really very clear on the system is if the slope there is greater than the prescribed value, our engineers discovered that the likelihood of failure is less than 10%. Just calculating it again and again, you can discover, here it is, if I keep this design rule, very simple, the likelihood of failure is less than 10%. So I can move really, eliminate the CAE. And now, if the likelihood of failure is 7%, the table looks completely different. Now, the rational choice, the option with the lowest expected net cost, is do nothing. Of course, if you want really still, if I would be in our quality or marketing and sell the cost of the warranty, which is not big in this case, but the lack of satisfaction of the customer will cause me maybe to do CAE too. But this is a different decision. We know what we are doing and how we are doing it and what is the cost. And of course, where the chief engineer wants to put his money, here or somewhere else, because we know the money is finite. So with this, really, in the intersection of design and risk, we know that we already proved to ourselves that we are wired to make the wrong choices. Decision analysis can help us. We cannot afford to analyze everything. This is really important too. And failure is an option. Failure is an option. We don't need to do a test. We can use design verification process, and with the tools like Bayesian Inversion and other, apply it rightly to the verification. Thank you. And you can see that I'm still playing a role.
Richard, thank you very much. We have time for a few questions.
I was afraid of that. Go ahead.
Thank you for this. You spoke of the cost as in learning.
Oh no, there is this loop which we were trying to show, and sorry I didn't talk about it much. The return of the FMEA, which you do, and by doing it the right way, from failure, you learn how to not to fail. The good example was on the error induction system. By failure, we calculated the slope. We know now what the slope needs to be, and we are preventing completely failure. Sorry, I should have mentioned it more. Go ahead.
How did you convince Ford to do the counterintuitive thing? I mean, you're right, we're hardwired to make the wrong choice.
By the Monty Hall problem. We presented it to staff after staff, and they make the decision exactly like this room. And started asking them, just a second, maybe we didn't do. The reality is that this is being today used by GM and Ford, not Ford only, by Boeing. And it's being used to make major decision. Investment in program, which program, how to do program, what are the right attributes of a program, and so on. Those are bigger, really, financial decisions which we are doing. And there we are using something which I didn't show here, which came from the Army, war games. The practice of war games and doing a complete simulation of really position to make the right decision. Here, it was more on the minor part, how to put really new thinking process into the engineering and really to make rational decision, because the engineers are staring really at the DV plan and saying, okay, which one I should do,
Right.
what I should do. Having the best CAE sometimes is not exactly the answer.
George Wang from Bowen. It was very interesting that you have design standard. In there, you put zero cost. In my experience, design standards would help the downstream process. So the design engineers would do design for analysis, design for manufacturing, design for exchange, and maybe some design standards would do, well, what we have learned from years of experience, so it would be easier for some reason. But whenever you put a constraint and limitations to tell the engineers what they should, how they should model it, you tie their hands. I think there's a cost to it, definitely, but how do we measure the cost is the question.
So the reason I put zero cost behind design standard is really you pay, it's like every software vendor here in the room will tell you, you paid for it already. So this is really the results you are getting for something you paid. How you create those design really rules? By failure. You fail many times, you did the test, you do the CAE, you learn what the slope, for example, on error induction system should be, and now you have design rule, design it this way. This is the template. And you pay for it in the models before. Now you don't pay for it. And no, we don't limit the creativity of the engineer by doing that. All I'm telling him, look, if you will design the slope to be in this kind of a slope, your failure probability is 10% or less, and you can avoid really the cost of doing testing or CAE. This is all I'm telling him. I'm not really limiting him. If really the program decided that they want to completely change the design, they know that they will need to retest it.
The probabilities you need up front to support the decision making, can you describe the processes by which you get those probabilities and how much confidence you have in those actual numbers?
So I was trying to show the confidence which we have in those numbers, and made an example here of 2 or 3 cases. The numbers were real, the 60, 75, 90 didn't come out of air. Those were real numbers of real example. How we are got to this, I would try not to get into it, because this is really this is the heart of the proprietary, really, methodology we are using. We work very hard for many years to do it. It's being now in 3 or 4 patent discussion, and I don't want my competition to hear it. But yes, we develop methodologies, analytical methodologies to evaluate really the probability. It's very simple in a sense, just the way the casino is calculating. Think about it this way. I will give you not to get you my secret, I will give you the casino secret. They know, for example, in blackjack, that 51% is there, 49% is of the customer. This is it. It's very normal number of all the card combination which very computer can calculate. This is exactly something similar to what we are doing.
Okay, because my point is with finite element analysis, you consider the uncertainty in material properties, uncertainty in loading conditions, all of these different uncertainties. And
This is exactly what we did.
yeah.
And I can tell you that Belichko and others participated with us. So this will give you really from where it came.
Okay.
Excuse me, sir. Dave Ullman, Robust Decisions. I really enjoyed your talk. I have two questions. One is, you showed a plot very early on that had the technical, horizontal, and the social vertical, yet all the examples you showed in the rest of your talk were all technical. Where is the social part? The second part of my question is, I've been beating on the CAE industry for about 10 years, saying you need to include these decision-making methods in your analysis. You need to be taking into account the social. What do we have to do to get these integrated into the tools that we're providing to people like Ford and Boeing?
Two great questions. I did not include really you're right. In the two examples I did not include the social part. It do exist. The social part exists more on the decision really of picking attributes, and which are really another example which we can go through. What are the combination of option and how you are presenting them and what part of the system? Yes, those examples exist. I did not include them. The other really, if I wanted to achieve anything in this talk here, and the reason I was so glad to really get the invitation was exactly that, to send a message to all the CAE vendors, start integrating this kind of tools inside, because this is what is needed.
And with that, Richard, thank you.